for the disaster management. So today we will have the four lectures. One lecture from the 11 to 12, then second from 12 to 1, and the third lecture from the 3 to 4, and the fourth lecture from 4 to 5. So the first lectures will be delivered by Dr. Anup Kumar Das. He is a scientist at the Space Application Center, Ahmedabad. So he is a very renowned personality in ISRO. So he has obtained MSc, MPhil, and PhD degree in the environmental sciences from School of Environmental Sciences, Jawaharlal Nehru University, New Delhi. And he joined Space Application Center in 2005 as a scientist. And since then, he is engaged in the research and the developmental activities related to the applications of microwave remote sensing, especially synthetic aperture radar in geosciences and planetary sciences. He carried out scientific investigations using spaceborne SAR data as principal investigators of the ALOS-1 array, Cosmos SkyMet AO, RISAT-1 utilization program, Chandrayaan-1 mini-SAR, Chandrayaan-2 LNS band, dual frequency SAR, NISAR LNS airborne SAR data, and ALOS-2 data. Currently working on the development of the SAR-based applications for the vegetation monitoring and ecosystem dynamics. He is a member of the SAR task group of Forest Plus program, a initiative between USAID and MOEF and CC, Government of India, towards implementation of the RED Plus in India. And he's a member of ground segment committee and science team of the future NASA ISRO science mission, NISAR mission. And he's also associated with the development of science plan for ISRO's future planetary missions to Moon, Mars, and Venus. And he is a senior member of IEEE and life member of ISRS, ISG, and IMSA. And he is a recipient of the Green Asia Award, awarded by the Chinese Taipei Society of Photogrammetry and Remote Sensing in the year 2017 for his contributions to SAR-based studies on the monitoring of the forest above ground biomass. So currently he is leading ISRO's NISAR ecosystem team and developing SAR-based algorithms for forest above ground biomass estimation, forest disturbance monitoring, crop monitoring, and observing wetland inundation dynamics. He has published more than 100 papers in the peer-reviewed journal, and he is more than 3,500 citations. So we have very good, excellent personality with us today, and he will be delivering a lecture on the potentials and the overview of the NISAR missions and applications in the field of the disaster management. So thank you, sir, for joining us. So now over to you, sir.
Yeah, thank you, Hari Shankar, and it was a big introduction. Actually, I could have given you a smaller one. Anyway, so let us welcome all these participants. I cannot see online the participants, but I believe they are online. And I also don't know their background. If they have some exposure to microwave remote sensing, then it will be better for them to understand the presentation today. So without further delay, let me share my screen, my presentation. And just confirm if you are
Yes, sir.
seeing
It
my
is visible, sir.
presentation slides.
Yeah.
Okay. So basically, in this first lecture of today's workshop, I will just introduce to you the forthcoming NISAR mission. NISAR stands for NASA ISRO Synthetic Aperture Radar mission. It's a flagship program of NASA as well as ISRO in terms of its high potential to address several scientific issues and applications pertaining to land and ocean around the globe. Okay, so this mission actually is conceptualized from a earlier mission that is called Destiny by NASA, and the Destiny actually was a L-band SAR and LIDAR mission. and that couldn't materialize due to some problems with the mission. And later on, they thought to join hands with ISRO to develop a full-fledged SAR mission there. They removed that LiDAR sensor from that, and in place of that, they ISRO added one S-band SAR with L-band SAR with NISAR. And if you go to the background of this, actually this NASA first knocked the door of ISRO in 2011, 2012 time, when they uh, came to ISRO subsequent to the success of our ARISAT-1 program that time. Then ARISAT-1 actually make ISRO a SAR satellite capability space organization. With a SAR satellite in mind, the NASA came to ISRO for a joint collaboration, and ISRO was quick to respond, and it added S-band SAR with L-band to develop a joint mission that was named as NASA ISRO synthetic aperture radar mission. This mission actually was has a background to understand some key scientific objectives that includes to understanding the dynamics of carbon storage and uptake in wooded vegetation, our agricultural systems, our wetlands, and permafrost systems, and then to understand the response of ice sheets and glaciers to climate change, and how the interaction of sea ice and climate is taking place, and what are the major driving forces behind that, and also to determine the likelihoods of earthquakes, volcanic eruptions, land subsidence, and landslides. So all these things in mind, yeah, it was realized that a dual frequency SAR with very large swaths and high resolution operating in polarimetric and interferometric mode with a high repeat cycle can only address this type of science questions. So that was the birth of NISAR. If you look at the major instrument characteristics, the NISAR will be a polar orbiting satellite. It will be placed at exactly at for 747 kilometer orbit with 98 degree inclination from the pole. While placing the satellite with its specifications, then it will revisit a place in exact 12 days. And this nodal crossing time will be 6 a.m., 6 p.m. That means it will be a dawn to dusk orbit. That means in equator, every time it will the satellite will pass either in 6 a.m. or 6 p.m. And it has two frequency bands at 3.2 gigahertz. We call it L band, and at 1.25 gigahertz, we call it S band. And it has all combinations of polarizations available with the satellite, like single polarization, dual, then quad polarization, as well as hybrid circular polarization. Hybrid circular polarization was some we can call it a USP of ISRO, because it first implemented this polarization in ARISAT 1 mission, and it delivered some wonderful data and some wonderful applications. So that was implemented in S-band only, while the quad pole mode is there for L-band only. And other polarization modes are available both in S-band and L-band, and it has different bandwidth uh, available for this both the SAR systems. This bandwidth is basically, this is a band of signal that determines the um, uh, uh, slant trend resolution. Okay, higher the bandwidth, better will be the resolution, but higher bandwidth will result into more noise also in the data. So the noise equivalent sigma naught, that is the sigma naught sensitivity to targets, it decreases when you acquire it at a higher bandwidth to get high resolution. So resolution and the noise equivalent sigma naught, or what we call the backscatter sensitivity of SR, they are basically there is a trade-off between them. Then with these configurations, putting the satellite at 747 kilometers, it will achieve a swath which is slightly greater than 240 kilometers. And while doing so, it will cover the entire landmass in every 12 days without any gap at the equator. So that is basically one of very important feature of NISAR, that many satellites, they have similar repeat cycles, but actually they don't cover the entire globe during that repeat cycle. But NISAR with wider swath will do that. It is something similar to the Sentinel satellite, Sentinel 1A and 1B. You may be familiar with. So it is like that. And while doing so, it will achieve a spatial resolution. It's as high as 2 meter, and up to 15 to 30 meters in the lower side. Then it will be operated at a fixed incidence angle range. Unlike other satellites, they have various combinations of incidence angles. This NISAR will be operated at 33 to 47 degree incidence angle. This makes the data, the temporal data, very consistent. So whenever you one gets a NISAR data in a time series, it will be assured that the incidence angle is constant for all the images. And the noise equivalent sigma naught to than minus 25 dB. And those who are familiar with SAR backscatter signatures from land and vegetation, they will appreciate that this minus 25 dB noise equivalent sigma naught is excellent, is quite good for all kind of land and ocean applications. Then the major advantage of NISAR orbit will be its pointing accuracy. This pointing control will be of the order of 273 arc seconds and less. So this actually helps in acquiring data in interferometric mode, and it will have a very short baseline while very accurate interferometric capabilities. And the orbits will be controlled by a GPS and other gyro mechanisms to have a orbit separation between any two orbits is less than 500 meters. That means it will always have a very short baseline for interferometry. And this pointing, basically it is the look side of a radar. Radars are basically left looking or right looking. So here the pointing is fixed at left looking for NISAR. After a lot of deliberations and discussions, the scientists realized that most of the existing or past SAR missions, they have given much importance to the North Polar region, covering more data over there, and the Antarctica region in the South Pole has always been neglected, because people basically they collect the data from the periphery zone of Antarctica, and nobody has cared to take the continent ice for Antarctica. So NISAR thought that it should give more focus to Antarctica continent ice, sacrificing some area in the North Polar region, because when once you point your satellite to a particular direction, then you cover more data toward the pole of that side, and while sacrificing the other polar data. That means if pointing is toward the left, then up to 88.5 degree latitude, it will be able to collect data from over Antarctica, while the same the polar hole will be much bigger in the North Pole. That means in the North Pole, it will cover not more than 77.5 degree latitude. So from 77.5 to 90 degree, there will be a big data gap. Um, so this is a trade-off, and this what makes the NISAR unique is it will have a free and open data policy like Sentinel one, and the mission duration will be minimum 3 years, and it can go up to several years depending upon how well it can consume during its launch and during its operation. So basically, the fuel is the main thing that determines the life of the satellite. So if very precise launch happens and satellite doesn't require any maneuvers to attain its final orbit, then it saves a lot of fuel. So that fuel determines the life of the satellite. Okay, so the mission duration could be several years based on that. Then this L band and S band radar signals actually they pass through the ionosphere of Earth, and ionosphere basically it contains some ion there. The electron density is quite high there, so that basically affect the radar signal. Okay, radar signal is nothing but the electrical signals, so they get affected, and this impact is more on larger wavelength systems. So L band will be impacted more towards for in the ionosphere. So in order to mitigate that, this L band will be operated at different split spectrum methods. You can, if you can see my mouse cursor, then this L band bandwidth will be split into two bandwidths, one longer and one small. These differential bandwidths will be used to compensate for any distortions that happens during ionospheric um, you know um, impacts. Okay, S band perhaps doesn't require that. It is quite unaffected by this ionospheric disturbances. So S band doesn't have those split spectrums. If you look at the overall consequences of these specifications, then we can conclude that this L band of NISAR will be very useful for low temporal decorrelation. As you know, the two data sets, if they are acquired at two different conditions, then they show temporal decorrelations. Okay, and those conditions are have less impact on S band, L band as compared to the S band. For example, any change in moisture, any change in roughness due to growth in vegetation, or any change in roughness caused by some anthropogenic activities will have less impact on L band data. So L band is basically shows low temporal decorrelation compared to the S band, and so this will help this L band no L band will help in that. And while S band is more sensitive to light vegetation. Okay, so L and S band together will address a wide range of vegetations to be studied. Then this sweep-SAT techniques, we'll learn about this. This is basically is the technique that enables collection of image at a larger swath with high resolution. This will enable global data collection. Otherwise, it was not possible to collect global data within 12 days, uh, you know, for the satellite. Then those polarimetric combinations like single, dual, and quad will enable better surface characterization and biomass estimation. Those who are familiar with Sentinel, they may appreciate this, that Sentinel has very fixed polarization modes for its observation. Like in Indian region, we only get in VV and VH polarizations, irrespective of targets. But NISAR will have different polarization modes for different targets, catering to different type of applications. So that makes NISAR better than Sentinel-1. Then this 12 days exact repeat cycle will enable rapid sampling. Today most of the applications, they are focused on time series data. If you have a good and reliable and stable time series data, then you perhaps don't require more complex data systems like polarimetric, or maybe differential interferometric, or maybe polarimetric interferometric data sets to do any application studies. So this 12-day repeat cycle will provide you time series data, very reliable. Then this high resolution will enable in small scale observations, and this pointing and orbit controls will enable no differential interferometric studies to measure any minor changes in the land or ice surface that can be detected through this. And this is the configuration of the NISAR satellite. And this satellite will have a large, the unique feature of this satellite is this large wire gridded mesh antenna. Okay, this is basically, it's a 12 meter diameter circle, and it has you can see the frames here, and this yellow color is basically the wire grids, which are basically a wire mesh is placed there, and very lightweight reflector. And unlike a satellite radar satellite that transmits from the radar structure to the ground, here the radar instrument structure will first send the signal to this big reflector, and this reflector will enhance that signal and send it to the ground. And the receive mechanism also will be uh, through this 12 meter reflecting antenna. So that is how it gets very wide swath imaging. And this same satellite, you can see this is the reflecting antenna. This is a 9 meter boom through which the antenna is connected to the satellite structure. And this is the radar instrument structure, and below maybe behind that in gray color you have the satellite. Okay, and then the solar panels here. Okay, here the red lettered eh, components are basically developed by ISRO, and the green colored components are developed by NASA. So you can see this reflector antenna, this radar boom, this radar instrument structure, this L-band electronics, and L-band RF feed, all those things are provided by NASA, whereas the satellite, the solar panels, the S-band electronics, and this S-band RF feed things will be provided by ISRO, so that they both of these organizations will have equal share in the satellites. And in stored position, the satellite looks something like this, because once you launch it through a rocket, the satellite has to be compacted. It has to be folded to fit in a heat shield of a launch vehicle, and there after the launch, then this deployment will take place. The solar panels, this large reflector antenna, and some other instruments like this receiving antennas and other structures also, they will unfold. And if you look at this diagram here, this is the sequence in which the satellite will be unfolded. In the stored position, it will be kept like this in the rocket, which is basically a GSLV Mark II rocket. It can send up to 4 tons of mass to that kind of orbit of 747 kilometer. And NISAR is just 2800 kilometer. It is nearly 3 tons satellite. But in terms of remote sensing satellite, this is quite heavy because it is nearly 3 tons. So in the stored position, it will be like this, and once launched, gradually it's these reflectors the solar panels, its data transmission receiver, antennas, they will be unfolded, and it will take several days to do that, because this is a very huge structure and these processes are very slow. These are some of the photographs of NISAR being integrated in NASA and ISRO laboratories. Earlier NASA laboratory, you can see this is the radar instrument structure. Inside that, there are a lot of electronics feeding signal to the S-band and L-band systems here on the top. And this instrument structure, along with the radar reflector and boom, was transferred to ISRO in early 2023, and since then it has been integrated. It is being integrated in ISRO integration facilities in Bangalore. You can see the huge structures. This is the satellite bus, and these are the solar panels, huge solar panels, and it is undergoing various thermal and vacuum and vibration tests here in the ISRO integration centers. And this is the total NISAR satellite with all components there. This is a recent photograph. You can see the radar instrument structure, this 9-meter boom, this 12-meter reflector. It's folded here like an umbrella, and the solar panels are attached to it in a collapsible manner and to be deployed. And if you look at this radar measurement technique for NISAR, NISAR basically uses a very innovative technique called SWIPSAR. Through this, it attains a high resolution and high large swaths. Always there is a trade-off with resolution and swath with radar. If you have a very high resolution, then swath has to be very small, and vice versa. But SWIPSAR actually broke that trade-off. It's with this reflector antenna and the digital beam forming, as well as transmit on receive onboard processing systems. These sweeps are actually is able to produce very large swath, yet with very high resolution. So basically, those who are familiar with this radar imaging techniques, they can understand that SWIPSAR is a combination of this ScanSAR as well as strip map mode. Okay, so those two things were implemented in ARISAT satellite, but with two different modes. In ScanSAR mode, you had very low resolution, and in strip map mode, you had very smaller swaths. And this happens actually like this. This large reflecting antenna will transmit a large beam towards the ground, covering almost 275 kilometers swath. And from each of the subswaths, there are some 24 subswaths shown here, depending upon the number of elements of S-band. From each subswath, the reflected signal will go to the antenna, and a portion of this antenna will be illuminated. And for each subswath, a different portion of the antenna will be illuminated. And these signals, these 24 received signals, will be integrated there through digital methods and sent to the radar instrument structure, where this data will be processed to a seamlessly single swath of 275 kilometers. And out of this, the near range and far range elements will have little noisy because of its property of radar, so that a qualified swath of 240 kilometers will be cut out from this, and thus we get a higher swath with better noise equivalent sigma naught as well as higher resolution. That is the SWIPSAT technology. And as I said, this orbit of the NISAR will be very, very stable. NISAR will use very sophisticated GPS, star sensors, as well as gyro mechanisms, so that it will the following orbits and repeat orbits will pass through the previous orbits very precisely. So much so that if we draw a diamond in the space with a horizontal and a vertical distance, this orbit will always pass through that diamond. And this diamonds, this horizontal and vertical separation is just 325 meter to 250 meters. So you can see how precise will be the NISAR orbits. So those who are familiar with interferometry, they will understand that this is called a very short baseline interferometric orbit. Okay, with a very short baseline, one will not be able to do a digital elevation model from the interferometric analysis, whereas these precise orbits will enable a very high accuracy surface deformation there. So NISAR data is not optimized for DEM generation, but it is highly optimized for detection of uh, um, very precise surface deformations. Okay, so that is the uniqueness of NISAR. And NISAR launch actually is being little bit delayed due to some complexity in the structures and systems. Earlier it was destined to launch in October 2024, but currently actually the launch is rescheduled to February 2025. So considering a launch of NISAR in 30 January 2025, the NISAR will have its operations like this. The initial 90 days will be dedicated as the NISAR commissioning phase. During this commissioning phase, as you can see here, the NISAR various deployments will take place with the NISAR. First, the solar panels will unfold. Then the radar reflectors will detach from this, and it will be deployed. And then other systems also will be switched on one by one, and it will collect data, and then gradually the data will be calibrated, and the satellite will attain its reference orbit and start providing calibrated data. So this entire process will take 90 days. So these 90 days will be utilized for various diagnostic mode data collection as well as calibration. Okay, so from 90 days to 240 days, that is for another 5 months, this satellite will undergo various science calibration and validations. This is basically the nominal science operations. That means from 90 days, 91 days onwards, the users like the general public will start getting NISAR data, fully calibrated NISAR data. Okay, but the scientists involved in the NISAR project, they will utilize these 5 months to calibrate the various science and application products they are developing from NISAR data. So those products will be subsequently available to the general public for further processing and utilization in various other applications. And after this 3 plus 5, 8 months, the NISAR will be declared as its science phase, and it will continue for another 3 to 4 years, maybe 5 years, and it will collect the data as for a predefined observation plan. And when we use a system like SWIPSAR to get high resolution large swath imaging, it also has some demerits. Demerits in the sense, in order to achieve a very larger swath in high resolution, you have to transmit the signal intermittently, and this transmission, you can see the pulse width of this transmission is quite large. So in terms of microsecond, it is 1200 microsecond. That means for a 1200 microsecond, it has to transmit this signal. Okay, and it's also continuously receiving the reflected signals in between. So, and the receiving signals are basically uh, smaller in duration compared to the transmit signal. And when it transmits, a radar by its property, it cannot receive at that moment. Okay, So when it transmits, the receiving window has to be closed. So that brings a data gap in the reception. Okay, you can study this animation here. Whenever there is a transmission, like this blue polygon, when it reaches here, then it transmits. Then it receives from the subswaths of these systems, and it has not received it completely. Then again another transmission phase has come. Okay, so this brings a gap in the image. So in the entire swath, you can see these colored rectangles here. This is basically from start to end, it is full swath. And within this swath, there will be at least three um, gaps. We call it as range, dead range gaps. So that occurs. So if you see in the image domain, you will see three such type of gaps in a swath of 240 kilometers. Okay, this is something not acceptable. So there are this gap mitigation strategies are there. So it happens with any NISAR mission technique. So there are different ways to mitigate these gaps. Either you take the second image by shifting these gaps. You can do this by changing the pulse repetition interval, and you can relocate these gaps here, so that in both the images, if you join them, you will have continuous data here, like it has achieved in these images. Okay, these gaps are of the order of no, um, 2 to 3 kilometers in the slant range, and ground range it may become you know uh, 7 to 12 kilometers. Okay, so there is another way of mitigating these gaps. These are the with the staggered PRI. The pulse repetition interval will be continuously changing during a swath, and it is called a staggered PRI, so that these gaps will fall randomly in the entire swath of image. Okay, but these gaps will be much smaller as compared to those large gaps, and in image it will look like this. Then the image processing will take care of this gaps. So further image processing, the smaller gaps can easily be mitigated through range and azimuth compressions, and you get a seamless processed image. So while in this process, actually you lost some of the sigma naught sensitivity, but this loss is small enough to affect any its basic needs, so that after this loss also it is ensured that you get a noise equivalent sigma naught of minus 25 dB for NISAR. Okay, the NISAR is good for many applications. This data, no, unlike Sentinel data, this will be L and S dual frequency, and this data will be collected over different targets with different modes. Okay, so those modes are not fixed for all targets. So that enables NISAR to cater to a lot of applications. They can be structured as ecosystem applications, then land deformations, and any kind of land deformations, then cryospheric applications. Then it has a great potential in the applications of coasts and oceans. It can respond to the disasters through its quick data delivery process, and it will also cater to many other applications, including geological, urban, and mineral explorations. In order to achieve all those applications, a very well planned this observation plan is required. Okay, so NISAR observation plan is one of the most well thought of and well planned system, and here all kind of applications with all kind of imaging regions has been considered and thoroughly scrutinized to develop different modes for different areas to be covered without breaking the temporal or the time series data sets. Okay, that means we hardly change any observation mode over a particular area to break any time series. And with a 12 days repeat cycle, a NISAR is likely to collect 30 sets of images over any landmass or ice or ocean surface. So those 30 images, we have taken a lot of care to make those 30 images consistent and appropriate for the major applications to be addressed over a particular area. Okay, for example, suppose there is a region of agriculture, then on over this agriculture region, we have taken care that a particular mode which is suitable for agriculture crop classification, that mode is selected, and that mode is continuously collected over the entire crop cycle. Okay, so without disturbing its temporalness. And for targets which are perennial in nature, so we have taken care that the time series is not broken throughout the year over that target. You can see a global map with different observation plans with L and S band. Similarly, for ascending and descending nodes, if we combine, then it's basically the double the no we double the revisit margin, so that in every 6 days we get one image over any particular region if we combine ascending and descending together. Okay, so depending upon the property of any region for its applications, these ascending descending targets are also defined with different modes. And in order to address targets which are which have more than one applications and that require more than one type of mode of data collection, so we have done that through changing this ascending mode and descending mode separately, so that you don't break the time series of 30 images per year. And this is basically one observation plan of regions of Indian interests. NASA's observation plan and NASA's applications is for the global region, and Indian applications is confined to the India and its surrounding regions like the SAARC countries and these oceans here. And also we have great interest in the Antarctica as well as the regions where Indian stations are present in Antarctica. Also we have interest in certain North Polar targets. Okay, so this is the observation plan over India, and in order to have a a very consistent observation, then a observation calendar also has to be fixed prior to the mission. This is something the NISAR will be operated as a predefined observation calendar, and during the mission, there will not be any change in the observation plan. Okay, like it happens with many other missions. So over what target, over what time, and at what mode the data will be collected, those are all things are predefined, and these things can only be changed with the mutual consent of NASA and ISRO science team members, and they will study the uh, changes required, and if they feel that it is essential, then only the mission will be commanded to change any mode. Otherwise, with this calendar, the data will be collected. And these are some of the examples of how this data is collected over Indian targets. You can see this NISAR scenes are typically, it's a follow a track frame system where each image will be rectangular piece of 240 by 240 kilometers. And you can see such data sets collected over India and its surrounding regions through ascending as well as descending nodes. Okay, ascending, descending nodes, their alignments are a bit different, but nevertheless, they can be combined for many applications as a 6 days repeat images. Since we have requirement of different polarizations over ocean, over land, over Himalayan region, over Indian Peninsula. Uh, uh, then we have different modes also defined for these regions. This is another example where we have targets of where high resolution is required, like the urban targets, like the areas more susceptible to landslides and land subsidence. Those areas are collected at a very high resolution mode. And this collection of data is one thing, and bringing that data to your desktop is another thing. So that is also very, very complex for NISAR, because NISAR will collect almost 30 terabytes of data every day, and globally, and this data has to be downlinked to ground stations and has to be bring back to a data archival and processing systems. So a lot of ground stations has been engaged there. So this basically shows the schematic of those systems there. This orange polygons are basically concerned to ISRO, and blue for NASA, and green for joint. That means the data first, okay, this is for uplink command process. ISRO will be handling the commanding of the satellite. So any command to be given to the satellite, that will be provided through ISTRAC missions, and in consultation with NASA JPL, which is counterpart of US for this mission. And the joint science team is always involved in any decision making of this. Similarly, the data it transmits back will be collected through various ground stations in Antarctica, in North Pole, in Svalbard, and in Hyderabad ground stations, which we have in NRSC. Those ground stations will receive all this data transmitted back by the satellites, and they will process and archive it in that centralized data archival system located at NRSC Hyderabad, and this data will finally will be disseminated. So these are some of the things there. I will not get into the details of this. So basically, it shows that we have a well-planned system to archive the data and disseminate it. Then NISAR products will be structured to different levels: level 0, level 1, level 2, level 3, level 4. These are basically the raw data and the processed data, like they are in other SAR missions. But the NISAR will follow a track frame system. This every rectangle will have a unique track and frame systems that will be processed as per its observation plan. But there will be certain rectangles that passes through two different modes of observations. In that case, we'll have a partial frame processing system there. Like half of the this swath will be processed to one mode, and other half to another mode, depending on if it passes through two different type of targets here. So those things is also there. So accordingly, the user will get a very seamless data over a defined target, without no have to be without have to worry about the mode at which the data will be collected. And the most important thing is NISAR will provide some higher level data types, like the large area mosaic data and the science products. These large area mosaics are basically, if you are familiar with LOS FNF data, then those type of data will be provided. These will be topographically corrected and backscatter normalized data at 20 meter, 50 meter, and 250 meter pixel sizes, depending upon the region over which it is collected. For the entire global landmass, the data will be at 20 meter pixel mosaicked. And for Himalayan region and certain Antarctica region, there will be coarser resolution data. And this science products, basically, these are basically the forest above ground biomass, forest disturbance map, active crop area and crop types, then surface inundation maps, soil moisture products. Those are the science products from ecosystem. Similarly, there will be science products from cryosphere like the dry, wet snow, then snow water equivalent, then glacier phases, glacier velocities. Similarly, for solid earth science, we have the line of sight deformation, then time series deformation maps. Then from ocean, we have the ocean surface wind map, coastal bathymetry map. Those type of science products will be developed from NISAR data, and these products will be disseminated as it is to the users for further applications. And for all these uh, product archival and dissemination, our ISRO's portal Bhunidhi will be used. So users can create a login here and access to the data from the 91 dates onwards for the level 1, level 2 products. For level 3 and level 4 products will be available subsequently, maybe after 1 year of this commissioning phase. And this users has different ways to access and download the data, either fully or partially. So this is the Bhunidhi portal. One can create a login here and access to the data. Like currently, people are using it for US for like RISAT 1A satellite data download, as well as Sentinel data also it hosts. So you can have a hands-on on this to understand how the NISAR data will be available and how you can browse through the data and download it. Then these science products are basically the products, specialized products. Those are readily be used for any applications. So such type of products will be developed from NISAR. User don't have to find a algorithm how to generate like crop type map, maybe biomass map, maybe water inundation maps. So those products will be generated and user can use it, like soil moisture product. That is one of the very important products generated from NISAR at 100-meter pixel size. Similarly, the products from cryosphere and ocean regions and will be generated. Details of these can be seen from a NISAR handbook that is available in internet. You can search that. And in order to ensure that the data is properly calibrated for development of any products or utilization in any applications, we have a very extensive calval plan that is spanning from India region and other parts of the globe to Antarctica regions. We have established a lot of corner reflectors as well as ground calval sites to develop calibration mechanism for NISAR data. And similarly, for calibration of this L4 science products, we have various sites has been identified and extensive data is being collected to test and validate our algorithms, products to ensure that they matches the quality that would be uh, required for further applications. And similarly, in the global region, we have a lot of CalVal sites, which both NASA and ISRO uses to calibrate their products. And the testing the NISAR performance tool is quite important to ensure that NISAR meets the expectation of its sensitivity that is projected here. For example, for solid earth, no any deformations, it is the uncertainty of estimation has to be 3.5 into 1 plus square root of L. L basically is the length of the event that takes place. For example, for a smaller landslide or maybe land subsidence, the scale is of the order of tens of meters. For large earthquakes, the scale is tens of kilometers. So the L value is taken between 100-meter to 50 kilometers and tested with the NISAR simulated data, and found that with respect to 3.5 into 1 plus L square uncertainty requirement, it can achieve 3.01 into 1 plus L square. So that means it's meets the specification. Similarly for other parameters also, you can see that it basically it shows that NISAR data is through simulations has been tested um, um, to meet its expectation of its data quality criteria. Similarly, for ecosystems products, where the NISA data is expected to address the biomass of 100 tons or less with a 80% accuracy, and it is meeting that accuracy with 93.5%. So it's in a nutshell, it says how useful this NISA data is going to be. Then NISAR has a urgent response plan. As you know, any satellite, it has it's a duty to respond to the disasters. So NISAR also will do that. But only thing is NISAR, unlike other satellites, NISAR will not change its observation plan for any urgent response. So whatever mode or whatever area has been identified for a typical area, so that data will be expedited for natural disasters. For example, the general latency time for a region, if 3 days, in case of natural disasters, that 3 days will be reduced to 6 hours, and NISAR will produce the data for the disaster response. So there is a well planned disaster response tool is there. We call it a smart tasking tool, through which the disasters are identified, and the command is given to the mission team and satellites collect the data in a fast in a priority basis, and the data is processed through a priority basis and given to the concerned authorities through a completely automated process. So that is the uniqueness of NISAR system. I think with this, I will stop my presentation here. The actual utilization of NISAR data and its applications will be deliberated by subsequent lectures. So this is basically, in a nutshell, I would say that NISAR is a very powerful and yet very user-friendly system to cater to all kind of applications. Actually, you can think of uh, over all kind of land applications, and it will also cater to the disasters. With that, I thank you for hearing.
Thank you, sir, for delivering this very good lectures on the potential of NISAR's data sets for different applications. So,
if I can take up one or two quick questions if they have, or they can reserve their question to ask for the to the other lectures.
okay, sir. So they will send through email or something other way, or I will send all these questions. Then we'll answer those questions, sir. So actually now another lecture is scheduled. So
Sure. I understand that.
okay, sir. Thank you very much for delivering this lecture.
Yeah, thank you very
Thank,
much.
thank you.
a one-day workshop on NISAR application for flood hazard. Uh, so this is basically, in the first lecture, the overall NISAR mission has been covered. What products will be developed, how they will be delivered, and what are the mission objectives, and what are its characteristics, all has been discussed in detail. So I'll be focusing on the flood hazard aspects, covering some of the fundamentals, how SAR behaves with flood, and where all NISR can play a role in improving the flood hazard and associated inputs that are required for flood hazard studies. So let me introduce myself. I am CM Bhatt, working as scientist in Disaster Management Sciences Department, Indian Institute of Remote Sensing, IIRS. So let us first, because there will be a lot of attendants who are attending this course with diverse backgrounds, and some of you may be having a background on hydrological or flood related aspect, and some of you may be having some understanding on the space based observations. But before I begin, I just introduce, flood is a relatively high flow of water, and which the channel is not able to accommodate, in times of heavy rains, or there is excess of water which maybe due to cloudburst or some flash floods or some other or other anthropogenic causes, and this leads to flooding. So there are a variety of floods, that will not go much into detail, but riverine, flash, coastal, urban, these are the kind of floods. And generally, floods are on an increasing trend if we see the global estimates, and it is one of the main, main disaster which causes deaths, people to be affected, a lot of displacement happens, and economic losses because of floods. And your Southeast Asia and India is very chronically affected by floods. Now, where I know, because floods are having a regional nature, we require data from Earth observation satellites in every phase of flood hazard management, be it preparedness, relief and rescue operation, mitigation measures. So each phase, satellite inputs are required, whether they are used for forecasting, modeling, response, or post flood, whatever mitigation measures we are trying to have, and some of are listed in this particular slide. So now let us come to the main. This we require remote sensing data or satellite data is basically when we look for flood hazard aspect. It is mainly required to have the spatial extent of inundation, the flood persistent, the flood progression, recession, and how that is the temporal pattern of inundation. This is where we require satellite data. And apart from direct mapping of floods, other place where this data plays a critical role is the hydrological models, where this input is used for model calibration or validation and for data assimilation. Because we have direct observation from satellite data, and the hydrological model output can be validated or calibrated using satellite observations, and this is one of the main place where satellite plays a larger role. And once we have flood inundation from satellites or hydrological model method, we can go for flood risk assessment, which requires hazard, exposure, and vulnerability. So hazard is one of the most critical input that can be derived from satellite remote sensing. Now we have my optical and microwave imaging are the two modes that we generally see when we are looking for flood mapping or flood hazard. So as we all know that optical sensors are not able to fulfill the need because of their daytime imaging capability, and also due to shorter wavelength, the incident radiation is being hindered by the presence of clouds, whereas microwaves can operate in any kind of weather phenomena, and also can observe in day and night. So therefore we are able to have a better picture or a continuous picture which is required for the flood hazard monitoring. In this picture, as you can see, both optical and microwave, both images are acquired on the same day with a little time lag. But on the left, the optical images do not allow to see the flooding that is happening because of the presence of cloud cover, whereas on the right, we can see the floods because the longer wavelength penetrates the cloud cover, and we are able to observe the phenomena. So that is why this microwave imaging, which does not depend on the source of sunlight but has its own pulse, which can illuminate the ground, is has plays a very meaningful role. Now, we will not go much into the optical, but we know in optical also bands are there, and whereas in NIR is mostly used, near infrared is mostly used to discriminate between land and water, because NIR gets completely absorbed, and that's why we are able to discriminate between land and water. And just this is a picture to show you that in NIR band you can see the water much clearly, and compared to your green and the red bands, the land and water contrast is very clear. But this because since it is a part of optical, we'll not go much, and now we'll go to the microwave imaging part. And as we know, there are in microwave also there are different wavelengths are used, and there are different bands: X band, L band, and C band, and also S band, P band. But mostly you find satellites operating in X band, C band, X band, and L band. So this is slide shows you the missions that are in operations, and that or which are which have been phased out presently. Uh, Now, why NISR is one of the missions which is of very prime importance, because uh, it is one of the important features of the mission. Characteristics are its wide swath, high resolution, 12-day repeat orbit cycle, and dual frequency. It operates in L and S band, has a capability, and that's so. And this is a very mission that all of us are waiting. That once it gets operational, it will help especially the disaster management capabilities, and and also the monitoring of hydrological hazards. Now, what are the characteristics that basically influence the backscatter of in SAR images? Is that frequency, the wavelength, polarization, incidence angle? These are radar observation parameters, and combination of wavelength, incidence angle, and polarization plays a major role in influencing the interpretation to segregate flood areas from the non-flooded ones. And also there are certain properties like surface and terrain parameters, roughness, terrain relief or wing geometry, and dielectric properties. Now, radar can measure amplitude, that is the strength of the reflected echo, and phase position of a point in time on a waveform cycle. A radar can only measure part of echo reflected back towards antenna, that is called backscatter. Strength of reflected echo is backscattering coefficient sigma naught, and which is expressed in dB. One of the most important, one of the parameters that influences is the frequency or the wavelength. Wavelength is nothing but is equal to speed of light upon frequency, and wavelength is inversely proportional to frequency. Higher frequency means shorter wavelength, and lower frequency means a longer wavelength. And in SAR we have different bands like K, K, KU, X, C, S, L, P, and generally C band is most widely used, 3.8 to 7.5 centimeter wavelength. And we are speaking now of the NISAR L and S band. S band having 7.5 to 15 centimeter, L band 15 to 30 centimeter. So S band is having a wavelength higher than C band, and in between C and L band. So it has a characteristics which will be both in between C and L. And L, it is 15 to 30 centimeter. It is a longer wavelength. So how these properties will affect our interpretation, we'll see in coming slides. These are some of the missions: PLSCX, X band we have TerraSAR X, Tandem X, Cosmos SkyMat, and C band, Sentinel-1, NBSat, RADSat. S band we have one Chinese satellite, HJ, NovaSAR, from Surrey Satellite Technology. NISAR will have S band. L band we had earlier missions like CSAT, JERS-1, ELOS Pulsar, ELOS-2 Pulsar, SAOCOM. NISAR will also have L band. Now, once it comes to wavelength, how wavelength, as we saw in the previous slides, that since L band will be having a longer wavelength as compared to X band, so we will have a better penetration of the incident pulse, and it will have greater sensitivity to the vertical structure of the vegetation. Therefore, this L band is mostly going to influence our understanding wherever we have a dense vegetation, or wherever we have vegetation and we have underneath flooding in those areas. As you can see from this X band, the gets backscattered from the top of the canopy. C band has a moderate penetration, and L band has a longer penetration. So now you can see on the right these described on the right side image: X band, C band, L band. Now if you're using X band, it is just does not penetrate as compared to L band, and L band can give us the information of the underneath flooding. So L band is suited to detect inundation beneath forested canopy. Longer wavelength penetrates the forest canopy and interact with larger structures such as trunks and larger branch of trees. C band is useful when the canopy is sparse at the initial growth stages, and if the density of vegetation is low. X band penetration is further limited, useful for sparse vegetation or during leaf-off conditions for wetlands in marshlands. So multi-frequency SAR data complements capability for the discrimination of flood underneath different vegetation types. So L band has a higher penetration capability, and it can detect the flooding, and whereas the vegetation is less, or it is a leaf off period, we can go for a C band, or other X band can. Now this particular slide shows you the how what I was telling about the L band. There is a water, it has penetrated vegetation and it has interacted with the water. How the signature will appear in the image. So this is an SMAP radar L band, L band data, where there is volume scattering by vegetation. It is shown over here by the yellow smaller yellow circle, where you are having a grayish tone because of volume scattering. There is no penetration, very less penetration, and all the incident pulse gets backscattered. Whereas in the case of this forest, where you have underneath water cover, the pulse because of longer wavelength, interacts with the water surface and gets there is a double bounce, and it goes back and recorded by the sensor with a larger strength of the signal, and it appears brighter. So even though this area is flooded, in this appears brighter, signature appears brighter because of the double bounce. And this in case of C band is not we are not able to complement this information, even though it is flooded, but this information is not complemented by C band as uh, can be done by the L band. So this is one of the cartoon or diagram to show you. This is a dry area, where, and this is the flooded area where we have the enhanced return if tree cover underlain by water. There is a double bounce effect. Smooth water surface, first the smooth water surface acts as a specular reflector, and it's again hits the vertical vegetation structures and is recorded by the sensor. This is one of the example, where the field photograph is also shown. This is by JERS L-band data. So this is a pre-flood season where you can see the river and there is no flooding. So you have a moderate or grayish tone adjacent to the river. And once this forest gets flooded, the entire tone of the area gets changed, and it appears very brighter. The backscattering is high and appears brighter because of the presence of water, and the L band having a longer penetration capability allows to penetrate. It is able to penetrate and get the signal. Signal gets double bounce, and we have this information. So generally, at the moment, whatever C band satellites are there and whatever flood maps we are producing, they somehow do not include the such kind of information where you have flooding beneath the forest cover or vegetated areas, because the C band or the X band is not able to penetrate. And this is what the L band NISAR will be able to produce the change in, or the improvement in the flood mapping estimates till, which are underestimated because the present mapping algorithms are made to detect low backscattering areas, or where we have a specular reflection. We are able to detect those areas only, or the threshold mapping techniques or whatever techniques we are using at the moment, they are not tuned to detect such changes. But NISR will overcome this mission, overcome this issue. Now this is one of the examples from L band interaction. This is L HH, and in L also, L band also, HH has a better appreciation of the flooded forest because of the double bounce and vertical stems and horizontal. It is able to pick better in HH polarization as compared to the HV. And if you see in case of C band, C band data over the same area and almost the same time period of February, we are not able to see such kind of tone neither in VV or VH. This flooding is not detected despite the area is flooded and the season is same because of the shorter wavelength. And this is where the L band will is going to make a difference, and we will have improved estimation of flooded areas. So that is the role of wavelength. That is where L band will, because of the longer wavelength, and surely S band will also improve our understanding of the flooded forest. Now coming to the other property, that is polarization. Polarization refers to the direction of travel of an electromagnetic wave. It is vectors to vertical. You can see vertical up and down, horizontal left to right, or circular rotating in a constant plane left to right. The direction of polarization is defined by the orientation of the wave's electric field, which is always 90-degree or perpendicular to its magnetic field. So now, by varying the polarization of the transmitted signal and receiving several different polarized images from the same series of pulses, SAR systems can gather detailed information on the polarimetric properties of the observed surface, which can reveal the structure, orientation, and the environmental condition of the surface elements. So we have different polarization, HH, HP, VH, VV, how the incident pulse is getting transmitted and how it is getting received. So, while most spaceborne radar systems are linearly polarized, it is also possible to create a signal that is circularly polarized on the transmission. So, some missions also have circular polarization. So, but so from NISAR, we are going to have a chord pole data. That means we will have data in all polarization HH, HP, VH, and VV. Generally, Sentinel 1, we are having dual pole data at the moment. So this is what, this presence of all channels or all polarization will again help us to improve our understanding about the flooded regions. Because HH polarization penetrates the vegetation canopy better than VV, as we have seen in the LL, that L band HH polarization data which I showed you in the flooded forest. So HH polarization was able to penetrate the vegetation canopy better than the VV, and when striking the water surface, it is most strongly reflected in comparison to VV polarization. While the co-polarized backscatter is more sensitive to the double bounce, the cross-polarized one is more sensitive to volume scattering because of its depolarizing characteristics. Combination of co and cross-polarized data may improve the identification of flooded vegetation, as the double bounce allows a better discrimination between different flooded vegetation types. And flooded vegetation is remains a challenge still today, to accurately map these areas, and that is where the chord pole data or different polarization will make a difference and help us to improve the estimates of the submerged vegetation. This is one example where you can see the HH and the VV polarized images. So multiple polarization and wavelength combination will provide complementary information, and for flood HH is more useful, as it is less sensitive to the surface roughness. So this is one of the example from again from L band data. If you see both L band and C band are compared, and data is from August or 70. One is from September and one is August. But if you see the L band HS data or the HP data on the top case, you are able to appreciate the water or the sea area much better than VV, or which is more sensitive to roughness. So that is where also HH will help us to improve flood mapping, because it will be less sensitive to the surface roughness, and we can have improved estimation of flooded areas, especially in cases where we have issues of wind roughness or such kind of issues are there also, this polarization, because of the availability of the L band and HS polarization, we will have a better estimation as compared to what we are having at present with with Sentinel C VV kind of data. Then this is one of the study that has been done using radar set chord pole data, which shows that if we use all polarization together, again we have an improvement in understanding or the mapping of the flooded areas. So since NISAR will have chord pole data, again we'll have an improvement in understanding of the flooded areas. This is one study where radar set C band chord pole data is used, and this C band chord pole data has shown that chord pole data is definitely going to improve the understanding of the flooded areas. So in the study, we try to compare a different kind of water bodies and submerged vegetation and their backscatter, and to some extent partially submerged areas were we were able to detect. And with with L band and S band, this understanding will further get improved. And uh, and from this study, you can see HH, HV, and VV, all these polarizations were used. And if you compare with the area estimate that we get from HH, is the highest, 400 roughly hectares, as compared to HV and VV, which are little less, but all have their own strength. Then, but if we used a combination of, if we use all combinations together, we were able to have a better estimate of the flooding, flooding, as if you compare with the reference, if you have any reference optical data or high resolution images for which the study was, you are doing. So your estimate will be more closer to what you have from the single polarization. But no doubt HH is will give you a better estimate. Now, since there are different polarizations available in will be available in NISAR data, so polarimetric decomposition is also another area where, L band fully polarized data classification will provide higher accuracy for flood mapping, as a decomposition of fully polarized SAR data will allow land cover features to be identified based on the scattering mechanisms, whether it is single bounds on specular or rough surface, volume and dihedral scattering or double bounds, rather than backscattering intensity information alone by single or dual pole. As so if we have the quad pole data, we'll be able to discriminate different kind of scattering mechanisms. So that is where, this NISR will help us to further improve our understanding of the scattering mechanisms. Then incidence angle, also plays a role in the our understanding of floods. And generally high incidence angle images are more useful to segregate between land and water. And incidence angle is nothing but angle perpendicular to image surface and direction of incident radiation. So, as we go from near to far range, we have improved, as the incident angle increases, our the interpretation of the water features gets improved, because in higher incidence angle, the segregation or discrimination between land and water increases. And the NISR aptly suits this particular requirement, and it will help us, those incidence angle also will help us to improve our mapping. Then next is a feature, that is on the ground, that is the dielectric constant. It is amount of water that soil contains. And high dielectric constant, if the soil is saturated, it will have a high dielectric constant, and more energy gets reflected. And therefore soils which are having a high soil moisture will have a higher backscatter, as compared to, with the soils which are dry, which will have a low dielectric constant and will have a low backscatter. So this, dielectric constant is also an important property, for any microwave data. And if you, as you can see in this particular diagram, as precipitation increases, your soil moisture also increases. And then as precipitation continues, the the soil gets fully saturated, and it leads to flooding conditions. And similarly, if you see the backscatter, initially as soil moisture increases, you have a higher backscatter. And once the soil gets saturated, it goes to specular reflection. So this kind of changes can be, observed from the SAR data. And since NISAR will have, this and S band which are higher wavelengths. So this will be more uh, uh, more better, will help us to understand this phenomena in a more better manner, especially the soil moisture estimation studies. Soil moisture is very important for any hydrological or flood related studies, because you know we require many models, or our flood understanding requires soil moisture estimation. And penetration depth of radar signal, generally, X band has a lesser penetration as compared to your L band, in the case of high soil moisture. So L-band radars are particularly effective in terms of the ability to penetrate the vegetation cover. So wherever have soil moisture are there, you also have vegetation, or agriculture areas will have a vegetation cover, and therefore for estimation of underlying soil parameters you require better penetration. So and our tropical areas generally have dense vegetation cover, and also a lot of cloud cover is there during the flooding season, which leads to the signal attenuation, and therefore L band will improve the understanding of the soil moisture estimation. Then there is roughness. This is the characteristics of the ground surface. The radar signals is primarily sensitive to surface structure. The scale of the objects on the surface related to wavelength determines how rough or smooth they appear to the radar signal, and how bright or dark they will appear on the image. Roughness of the surface, the rougher the surface, more brighter it will appear, and the smoother the surface, more darker the area appears. And this is how, in generally the backscattering mechanisms, if you see, we can have a diffuse reflection, specular reflection, and the double bounce. And generally in case of SAR, we have a specular reflection where the surface behaves like a mirror or a very smooth surface, and nothing goes back to the sensor, and the incident pulse goes away from the sensor, and it appears very dark in the image at microwave frequencies. Now if this already I have discussed. Now this is what we are discussing about surface scattering, volume scattering, and double bounce scattering. And this is where the L band is going to, or the S band is going to make a difference, in case of flooded forest, or in case of partially submerged vegetation. This is some of the examples that already I have discussed, but just to show you in one snapshot, if this is if you see the circle with number 1, where we have a moderate gray tone, it is a volume scattering. And number 2, where we have a double bounce, it is having a white tone, it is the presence of flooded areas. And number 3 is normal specular reflection, where the surface behaves smooth, and the signal goes out of the is not received by the sensor. And number 4 is the area where you have a rough surface, bare surface, or deforested areas, or agriculture, where you have a diffused kind of reflection. So these 4 kind of cases will appear. Now, in case of agricultural crops, where you have the case of partially flooded crops, we have a dry soil, then soil becomes wet, and then it gets flooded. So this is the kind of backscatter that happens. Initially the soil moisture increases, then once the soil gets saturated, as the soil moisture increases, it leads to double bounce, and then once it gets saturated, you have a specular reflection. So now NISAR will also help us to improve the wetland hydrology. Existing L-band SAR satellites which are in operation have limited coverage and observations to accurately capture the spatial extent and temporal variation of inundation over wetlands. Inundated vegetation can be observed by L-band SAR when woody vegetation vertically emerges from water surface, enhancing double bounce scattering mechanism, which is especially apparent in the HH channel. This already I had discussed, but an ISR project will measure inundation extent within inland and coastal wetlands areas at a resolution of 1 hectare every 12 days with 80% accuracy. So from this mission, we are going to have a regular, product which will measure the extent of inundation in inland and coastal areas also. And it will this product will have inundated vegetation, open water, areas that are not inundated, and indeterminate, which cannot be determined, or some having some issues. So with this kind of product is going to be a standard product that is that is from this is coming out from this particular mission. And this is very important, for improvement in understanding the wetland hydrology. And also we will have improvement in inundation mapping and monitoring. Why so? Because NISAR will be there, which will have L band, S band, and also will be having other missions, like data from RI said C band, and also Sentinel-1 C band. So these data sets, and NISAR, since it will be in open domain, so it can be complemented by other data sets. So we will have more the time series or the temporal mapping will improve from the because of the data availability from the L band and the C band. And we will have a better time series estimation of the flood progression, recession, or the flood persistence after the launch of this particular mission. Similarly, the understanding of the flood hazard zonation areas, which is one of an important non-structural measure, will also increase. Because till now, whatever flood hazard zonation maps are made, they only are having the specular. Specular, those are only mapping those specular reflected radiation. No, but this in case of once we have L and S band, we will have we can also incorporate the double bounds, or the flooded submerged vegetation, or the flooded forest. So these hazard zonation maps will get improved. Then one more area where this NISR will help in flood or the flood related studies is the coastal vulnerability. We have a lot of coastal, or those areas where there is development of infrastructure, and there is some surface deformation and changes are happening. Because INSAR will measure surface deformation by measuring the difference in the phase of the radar wave between the two passes. If a point on the ground moves and the spacecraft is in the same position for both passes, as you can see in the picture, that there is pass 1, and you have and in the second pass there is a shift or the movement in the ground. To such kind of movements or subsidence will be captured by the NISAR mission, and they are going to be very important for like coastal vulnerability. Land subsidence will increase the risk of flooding from the major rivers, and extends the coastal regions susceptible to storm surges and tidal inundation, especially when combined with sea level rise, severe rains, or storms. So the we are going to see a major application in the coastal vulnerability, where the land is getting getting subsided, or there is an increase in the sea level rise, because of various causes, maybe due to groundwater extraction, or maybe due to development of infrastructure, or compaction of sediments, or some other processes. So combining vertical land motion with sea level rise projection and storms or scenarios, it will help us to quantify the extent of flooding hazards. Another area where this SAR will make an improvement is the levee or the embankment and dams monitoring. Because again, because of the capability to measure, because of 12 days repeat pass, SAR interferometry, NISR will measure changes in infrastructure, ground movement along this is one of the example where levees that prevent, levees is basically structure which prevents the flooding. And if there is any kind of deformation, or any kind of subsidence happening, these changes are not observed through naked eye or on ground. Whereas such kind of SAR interferometry techniques will be able to capture this very small but movements which are very significant for the monitoring of the any changes that are happening in such kind of levee or embankments and dams, which are critical for controlling the flow of water, and any damage to these structures can lead to flash floods. So therefore these are very important. Flood damage assessment is likely to get improved with the L band and the S band availability, because of the better land use mapping will also get improved. Generally in times of the monsoon seasons or presence of clouds, we are not able to uh, prepare a better land cover map, and optical sensors are not able to properly provide information. And whereas in that time, because of the S band, L band, and by better penetration of the canopy and the biomass, so land use maps will mapping will get improved, and similarly the flood understanding and therefore flood damage assessment. Similarly, in case of flood risks, or computation of the hazard, or the damage to the agriculture crops, especially paddy and other crops during times of cyclones or the floods, will also get will see an improvement, improvement, and we will be able to have a better estimation of the damages. Then subsurface, because flooding is not only surface phenomena, because many subsurface features also control the flooding behavior, especially the underlying drainage or the paleo channels. This will be a very critical information when we are going for any kind of flood hazard mitigation measures, or we are having flood hazard zonation. So if you see on the left, you have a optical data from land side. On the right, you have a L band, data from JERS. So in this, on the left, because of the shorter wavelength, you are not able to see the drainage which is present, but only the surface signatures. But whereas because of the longer wavelength, we are able to see the subsurface complete drainage pattern, and this is very important. In times of floods, or the water will likely to have follow a hydrological slope, and follow the movement of water will happen along these channels. So this kind of information will be getting complemented. And one more example of this, if you see on the left, you have a sand, this is a picture of Salimat sand sheet example from southern Egypt. But if you see in the left, that is a optical data from spot image. You are not able to see any kind of drainage, but if you see on the right, there is a well developed drainage network that is able to be captured by the L band pulsar, which reveals numerous paleo channels hidden by a meter thick layer of aeolian sand. It is a sandy environment. And because of the sand, optical data does not provide such information, but because of the longer wavelength, pulsar data, so that is what we are going to see in case of NISAR also. A lot of such kind of observations, which we may not have seen because of such missions like NISAR, which will be publicly available, and a continuous mission. So lot of such new subsurface features or hydrological features may be interpreted, and maybe in a better continuity may come out, because of this can be see one more example from here. If you just see same sand sheet, I tried to also observe from the from the sentinel 1 data. So if you see the same area, but you are not able to see any data from Canes or the Pleiades data, that is at 50 centimeter. You see all entire sand only, and only some kind of geological structure is you are able, or possibly a fold is able to observe. But on the right, if you see from the sentinel 1 C band SAR data also, these structures are coming out well, and L band and S band may further help us to add more understanding of such kind of features. This is also one particular example where these are dry streams, and because of coarse alluvial gravel which are filled in this channel, there is more surface roughness and volume scattering, and therefore we have a strong backscatter and they appear brighter. So, and possibly in if you see in we are able, because of L band, we are able to observe these drainage network which we may not have seen in case of maybe in optical images. Other important thing is that because L band have a longer wavelength and S band have a longer wavelength, the signal attenuation by clouds and raindrops is going to be severely, they are not going to be getting impacted as compared to our X band or lower wavelength. So rain has greater effect on microwave than clouds. The effect is negligible for wavelength which are above 4 centimeter, but below 4 centimeter they get affected by rain. And degree of signal attenuation by heavy rain is inversely proportional to radar wavelength. That means the higher the wavelength, you have less attenuation. And with C band, which C band is also moderately affected. There are examples where we have noise on the, or there is obstruction by the raindrops, and X band is severely affected. And and at the longer L band, attenuation is generally not observed. So this kind of data improvement also will going to happen. These are some examples. And basically raindrops, or they are called hydrometeors, which consist of liquid or solid water particles. They cause both volume attenuation and volume scattering, which is a function of radar frequency and rain rate. And this example of X band, so we are able to you are able to see lot of a data set with dark, as if they are some shadows. Several shadows are accompanied by adjacent slightly bright patches on their near range side, due to backscattering of microwave by raindrops in the atmosphere. So this kind of improvement also will come. This is one of the data from C band. Data, if you see on the picture on the right side, it is also during heavy rains. You see features like cloud shadows on the picture, which perhaps are not clouds or neither any kind of water feature or neither kind of any shadow, but these dark patches happen to be the obstruction by the raindrops, which C band also gets gets the signal gets attenuated. But if you see one example, just L band and X band. See here, if you see this is from the old SAR C, X C and X SAR images acquired on the, this is on the X band. And L band, if you see, if you see on the X band, you have a lot of disturbance. The dark area in the lower right hand section, if you see, it is caused by the raindrops, which has attenuated the X band microwave signal. Whereas on the right, these are not, it does not have any effect, and you are getting clearly the drainage pattern, and also the all the features are clearly observed. So such kind of attenuation of signal, also and if you are working for floods, so this dark area may be misinterpreted as flood. If you see on the X band right side picture, this can cause an overestimation of the flood area, and perhaps which is not a signal for for the specular reflection. It is not an indicative of specular reflection, but it is attenuation of signal at X band. So these kind of improvements also will be in the quality of data, which will help. So there are many areas which will help to improve the understanding of the flooded areas, inundated areas, or the hydrological field. Many such applications will be there. So this I have tried to list out some of the areas where improvements will come. And with this, I'll conclude my lecture. And if any questions are there, these questions can be taken, maybe put at my mail ID. Perhaps I must have put in my first slide, or can be in the cmbhatt@iirs.gov.in, and I will be happy to answer, or can be put in the chat box. We can discuss at the end of the session today. Once we are concluding the session, we can take up these questions. Thank you.